project the triangle on the screen, and you keep something which is called the depth buffer to like always keep the closest objects. So that's kind of how rasterization works. So ray tracing is a bit different. So for each pixel you calculate the ray from the camera, and then you use intersection function for primitives. And you say you keep the closest primitives, and then you can shoot other ray for shadows and reflections. But the most important is the intersection function, really. And of course, the big problem with ray tracing is it can become pretty slow very fast, because as soon as if you want quite high quality pictures, you're going to need to shoot rays for like several rays for shadows, several rays for reflection, and reflect again, then you have refraction, so it can become really, really expensive. And ray marching is a bit of a variant, because sometimes we don't know the intersection function in analytical way. So what we do is we use instead a distance function, and instead of drawing this kind of line, we just draw segments. So we advance until the distance is small enough, and then the technique is more or less the same. It's just we use segment instead of functions. So it's quite a nice technique, because you can make both our basic CSG like intersection unions are really, really simple to do with ray marching. It's like min-max operators. And with random mass formula, you can have some quite funky results as well. So one of the big things about graphics is like most of the technique, a lot of people think, oh, we have this new technique, but a lot of techniques are not really new. It's like, for example, the first ray tracer, like one of the most popular was started to be programmed in the 80s, so it's not like it's not like new techniques at all. It's like even pretty old techniques, like shadow mapping, which is very popular in 3D graphics, was created in 1978. Cook Torrance, which is a light equation which is used in a lot of games nowadays, was done in 1981. Metabol function was in 1982, so it's not we do like necessarily new things. But of course, like all these techniques from before, it was really hard to do them in real time. But now we have like 10-15 years ago, processors power increased a lot, so we started to be able to do these kind of things in real time. But since a few years, they are more like stagnating. Processor speed doesn't improve that much compared to how it used to be a few years ago. But in the opposite, graphics card power is massively increasing. You have more core. You have like every year you have a new range of graphics card, which is much more powerful than the previous one. But it implies a bit of difference, because GPU, it's like they have. Processors are slower, but they have much more of them, which means you need to learn about parallel programming. And so that's how now you can modern graphics implies pretty much GPU programming, at least if you want to do it real time. And they even use it now in a lot of offline systems. So now, like, I'm going to speak more about rasterization, because that's the technique we use the most, because we use DirectX. So the early stage, you only had a fixed function, which basically means you set a view on projection matrices, which is just, that's your camera, and that's going to be normally a perspective. You set some render states. You can say you had a limited amount of light, so you say, I want this light here, I want it to be a point light. You could add fog and some texturing, and then you draw your geometry. So, but the problem is you can't really, well, you could already do nice things with it, but the problem is you're quite limited in some way, because you can't say, I want to change the light equation, because, for example, this light model doesn't fit so you could not do it before. So now that's how the rasterization pipeline works. So you have assembler, vertex shader, which is now like fully programmable. Geometry shader is fully programmable. And then once you have your geometry, it's projected on the screen, and then you can still program how it's rendered into pixel. So you have quite now like all those three stages are programmable, and it's like a direct extend, because now you also have a new stage here which is called tessellation. So I'll show you some examples of them in a bit. So for people who are not familiar with HLSL, it's just like a programming language. It's a little programming language, but the big difference is instead of running on the on your processor, it runs on the graphics card. So like every stage, so for example, for every vertex, your shader you can say how to process it. So you can transform it into screen space. You can change how your normals are. But so the first version was very limited. So you had a very limited instruction count, very limited feature set. So it was not that interesting. The second, which is called shader model 2, was like already, you couldn't even do branching. So for people who are familiar with programming, the standard if then else was not available really in HLSL1, so you could already do a bit of branching, but you didn't have vertex texture, which I'll go back to. But you could already do new nice things. So for example, it became possible to do blur in real time, some custom blending, a bit more advanced light model. So from this stage it started to become a bit more interesting. Then came Pixel Shader 3, which is the very, like it's a major improvement, because you have what's called floating, you could use floating point texture and vertex texture. So it's when all the big particle systems have started to be possible, because you could use texture to as data, which was a bit of a hack, but a lot of really nice things have been done with it. And that's the first time you also had multiple render targets, which allows deferred rendering, which is a very, like pretty much every new game uses this technique. So then it comes to DirectX 10 and 4, so you have new geometry shader instancing, new text, plenty of new way to do texture lookup like Gatter. You could render geometry, and you started to have compute shader, which I will also go back to. And that's the latest one now, which is 5, which has new shader stage again, like tessellation, like compute shaders are really been improved a lot. You have new way to use data, like it's very flexible. You can render volume, you can do indirect process, a lot of new features which have been brought, which allow, it's like, yeah, it's not you can do things necessarily faster. That's like one of the main things when you reuse, because the graphics card has this amount of power, so it will run at a certain speed, but it allows you to do things in a different way. So you can do things like in a much more efficient way compared to before. So that's the graphics pipeline. I go through it. Yeah, it's like, and that's the compute one, which is basically just a dispatch. I just passed through. I got quite a few, so I just probably go into some examples, because I think it will be a bit easier. So, like that's what I say, the render pass, the two main techniques are forward and defer. So forward is like, you just draw objects and apply light every time for every object. So it's like a lot of performance issue, but you can have some optimization. But the problem is you need to do a lot of permutation depending on the materials, which is a bit prohibitive. So that's just a simple example with few spheres on 20 lights. And now the deferred pass is a bit different. So you draw information and all the rest is done as post-processing, which allows you to use a pretty much unlimited amount of light-ish. You have a bit of anti-alias issue, which is not that true anymore. It's very texture intensive, but then it's much easier to handle material. So that's how a deferred renderer basic looks. So you have you render all your scene to 3 targets. So the first one is just the color. And I use the alpha channel for something which is called grossness, it's for light equation. Then you have one which is the normals, and reflectivity, which is also used for light, and then which is depth, which is provided for free, which is distance from the pixel to the camera. So then you can apply pretty much anything you want, so shadow, texture, lights, occlusion, fog, depth of field, tone map, blooming, color correction, so the number of post-processing is just limited by your graphics power. So I'll show a little example of a very basic one of deferred. Takes a bit of time to load. So yeah, that's just a simple thing. Yeah. So you just have a model on the shadow here. And you can see, for example, you can move a bit the camera around. On every sphere is acting as a light, so you can, there's 128 lights, which is not many. You can change their size, for example. And so yeah, everything is rendered through this target. So for example, I got here, I got my normals, I got my color, which is just plain white. So that's before the post-processing, basically. And that's after a bit of post-processing. I didn't put many on this one. And then you have also the shadow here. So that's a bit how a deferred looks like. And then you have, yeah, your obvious depth buffer, which looks like very nice. So all the, from all this information here that we can still like process and just start to generate a new way to do it. So now when we draw objects, like it's pretty simple. We give a few states, so we just say how objects are going to blend, how objects we want them to react to depth. Then we bind the geometry to the graphics card. We set whichever shaders we want for the processing, and we call draw. So to say draw my object. And for every object we repeat and repeat it again, which actually, if you use this technique, it's bad. Because you're going to end up in quite a major issue. Because draw all this, preparing this is costing a lot on your CPU. And like normally, like a very high-end game generally does 3,000 draw calls, and it's like very maximum. But like 3,000 objects on the scene is like extremely low. If you start to think about buildings with explosions and like in modern games, like a lot of character, lots of grass terrains. So you have, it's like very low. So so you need to be able to draw more. So there are several techniques for it. So the first one is called curl. So basically you have your camera here, and then you have what is called the near plane of the camera and the far plane on the camera orientation, and you convert. So what you do is you take each object, you use a bounding box for the object, and so if instead of you test the bounding box against every of these 6 planes, and if the object is outside, you can just say don't draw it, which is it's a very simple technique, but it works pretty well. Like for example, if I do a very small sample and just patch it, so I'll take a renderer. Set depth and timing, so we can see the frame rate. So and speed it up. Okay, and now I'll just add light. So we have a sphere, we have the camera. So now I'm adding more sphere, more sphere. You can check the count here. And I will just multiply. So I will pull them apart a tiny bit. And so here I got like 1,000. And I'll add more. Okay, so now, yeah, I got like 5,000, so my frame rate starts to go pretty much down. And now I got 9,000, and yeah, I'm already at 300, so this one is a good card. So now you can just say, first run, test. And now it tells you also how many pass the test and how many fail the test. So, for example, here I already just by adding test I gain like 10 frames. And if I zoom a bit more into, I can get a significant amount. So it's a very simple, it's a very, very simple way. If it's outside of the screen, there's no point of drawing it. So it's like you really, like that's the most basic way of helping your geometry. So now you can see also one thing is like, I got quite, like here I'm drawing an object and I'm drawing a lot of times the same object. So now you have, that's the second technique which is called batch. And the batch is like the most important technique in modern graphics. So what you do is, instead of, if your object is the same geometry, you're going to ask your graphics card, draw me, for example, instead of asking, draw my object once, like draw my object one time, draw my object one time, and repeat that 1,000 times, you're going to tell to your card, draw me this object 1,000 times. So if I do, I'll have a sample. Just use a little sample for it. So that one is just, yeah, I don't always use the light when, basically when I work. Like most of the time I just use normals for the rendering, because at the end it's going to go into deferred shading. So for the samples, it's quite very handy to know how to look at normals rather than anything else. So that one is like 3,000 fishes which are also skinned. So what I do is I say here, I bind here in a buffer, and I say, instead I have my geometry, which is just a simple, yes, it's a simple color file, and every fish is animated independently as well. So, and I just send their position into a big buffer and say draw me 3,000 times. So that's when you look in, that's basically how a shader looks like, by the way. So you can see here when I ask my graphics card, you have this thing which is called instance ID. So from there it will tell me, it's processed for every point, but this will tell me this is fish number 1, this is fish number 2, this is fish number 3, and it's provided to me by the graphics card, so it's not something I have to deal with myself. So from there I can retrieve the position of the object, I can retrieve the scaling transform, apply the scaling transform, apply it on the normal, get the position of the object in space, project it on the screen. But all this, instead of doing 3,000 calls, I do it in one, which is quite a huge time saver. So yeah, we use structured buffer and then we use instance ID, and that's more like 4 bits. Well, I'll speak about scaling a bit, because it's like when you animate characters, like you have two different parts. So the first thing is you have like an animation timeline which has been designed by a 3D artist. So it's just going to be basically the bones animation. So you have to look up in the timeline for the position and the rotation of the bone. So you need to do interpolation for the position, and you need to do a spherical interpolation for rotation, otherwise it looks ugly. And then you need to take all the bones and propagate it back to combine all the bones from local space to normal space, and then multiply by what's called inverse bin pose. And then you send the model and you batch them because you want to render a lot of them. I don't want 3 fish, I want an army of them. So keyframing comes with a little issue first. It's like when you look at a keyframe, it's linear complexity, which means if you have 1000 keyframes, you do potentially 1000 iterations to find where you are on the timeline, which is, you can optimize it by storing the current keyframe and look for linear playback, but well, for random time sake, it's not, you go back to this linear thing. So if you have 60 bones on 1000 characters, it's already 60,000 lookups, which potentially, so it's not that great. So for this, I've converted the keyframe list into what's called interval-based recursive tree structure. It's basically you get you just subdivide, so you have like it becomes a node based like a tree. So instead you have a node you can, like for 1000 elements you can access any timeline in 8 iterations, which is pretty handy. Actually I did that for database 15 years ago. I didn't expect it to use it for computer graphics. So you do your traversal for looking up, and it's very nice also because it has the same lookup count, so it's very fitting some parallel model. So for bone propagation, you just put a big array of transforms separately because it improves cache, but that's another. So you process all your transforms and copy all the transforms to a buffer. And we could of course curl the models if we want, but that's not always desirable. So that's pretty much how, so that one is still running half of the transformation in CPU. I got a few parts which are not done in compute shader, so like that's just inverse bin pose because it's a very simple multiply. So graphics cards are very good for doing matrix and vector mass, well, they're designed for it. So I try to offset as much as I can to the graphics card. So now I'm gonna go into a bit more advanced thing because it's for the moment it's fairly basic. So one new nice feature you can use in from 10 onwards is texture array. So it's a bit like, it used to be like volume texture. So a texture is just, you can think of it as an image. So a volume texture is like a 3D image. So every pixel is in 3D. It's called a voxel. So one big advantage is if, for example, I want to bind 4 textures, I need to create 4 pins in my shader. But instead I can combine them in an array and access it via index. And you have like, so I don't need to sort anymore, I don't need some ugly things. And well, you have a penalty for lookup time because obviously it becomes a 3D texture. But it depends on hardware. Like on the desktop it's not that bad, but on the laptop it's very bad. But then, well, we can use like depth prepass, which I'll also show. So it works really well with instancing because you can, for example, send 1000 objects, and if you have 4 textures, you can say this object is number 1, this one is 2, this one is 3. So, like that's the example I'll show. So I create an array, so I send video texture, in that case it's 6 layers. And I have a big array of masks which are multiplied. And then I get a dynamic buffer which says texture 1, texture 2, how much I want to blend each, and the mask index. And it gives something like this. So you have quite a bit. So yeah, you have quite a few boxes around. you have 6 layers of HD as well. So it's running kinda nice around. It's like 48 frames per second. So like the floor of the city, if I reduce, because it's all dynamic. So just the floor here is 160,000 boxes. Oh, and what's happening? And graphics card saying that I'm not happy. Yeah, very well. So yeah, that's the city when you have nothing on it. So yeah, you can quite zoom into it. So to create the city, it's a very simple compute shader. So I receive the position of every box which are just to the floor. I create a noise function and I apply a power function which adds, it's like a instead of having a linear curve, I change it to non-linear, which allows me to have a bit more contrast in between. And after, I just append more boxes, so I just generate more object out of it, and then I send it back to the graphics card through indirect draw, which is something I explain later, and that gives you a total of 900,000 boxes running around. And so here you have also, like I got a small buffer of 2000 because that's enough for randomness. You create, so this one says take a random texture number, take a second random texture number and blend them, and that one is the number for the frame. So if you look in batch here, so in the batch here I grab the data here, and in the pixel shader I grab like the video sample here, video sample 2. I just take that's for the frame, like this, and I just blend and multiply by the frame, so it's quite simple. And one other part in there is I use what I call a depth spray, because the problem is it's really pixel intensive, because you do a lot of sample on a lot of texture, and if you're in the wrong side of the thing, you're going to have a lot of wasted pixels. So what I do is what's called a depth spray pass. So I take the first depth buffer here, I just render the geometry, but say ignore the pixel, just write my depth, and I rebind the depth buffer as input. So that means only the pixel which have passed the test before will be allowed to do the lookup. And if I remember, like on the low end, like on my laptop, for example, it goes from something. On this card, it's like just so good, it just eats it like very happily. But on the lower end, I had my laptop was 5 frames per second up to 45. So in that case, when you have very pixel intensive, this kind of depth pre-pass come in very handy. So yeah, you can of course animate it if you want, like faster. You can change frequency, of course. So yeah, you can also change all the parameters pretty much in real time, which is quite really nice. So it's a bit too fast for me. So that's one of the examples. And yeah, one also interesting thing is like now, because the problem I have here, I think, well, actually I'll explain it on the next sample. So that's more stream output. Okay, I show a few. Okay, I show just a quick tessellation patch. So because like people think about tessellation only in games to improve with displacement map, but you can also do some pretty funky stuff for generative graphics. So that one is just like that's the splines renderer. And so what I do in this one, I send data as control points. So it's like 1,000 points to the graphics card, but it's obviously quite slightly more geometry than this. And what I do also, I use what's called a null drawer, which is like you can tell, like normally you need to send vertices or indices to your graphics card, but here I just say to the graphics card, draw me 1,000 of nothing. So I just say draw me 1,000 times nothing because, well, you have two ways to do it because the data comes from somewhere else. So I don't have any geometry to give you, so draw it and I'll deal with it later. It's a bit way to do it. It's a bit confusing for people sometimes, this feature, but it's very powerful actually. And so that's how then you get into the tessellation one. So I get the control point, so it goes first into the vertex shader, which just say that's my input for the in the graphics pipeline. It's called vertex ID, and so that means you are nothing number 1, you are nothing number 2, you are nothing number 3. Then so what I do is I just pass the nothing index to what's called the hull shader, which says I'm control point nothing, and then I use this, which is called tessellation factor, which means convert my nothing into n nothing. So instead of having 1 point which still doesn't have any data, I can say you can have between 1 and 64. So, and then you arrive in the domain shader, which is where I start to get the lookup time. So I can just say, no, okay, you're number 1. So I do the lookup in my control points, and then I apply the functions for it. So it's just a b-spline cubic function, which also gets the derivative for the normals. And then my nothing becomes a line. Next, it arrives in here. And then it arrives in the geometry shader, which basically says, oh, I receive a line, and I convert it to some kind of cylinder, but then I can change, for example, it's like a triangular cylinder, but I can all change the settings a bit as much as I want. I can say, if I increase the resolution, decrease the resolution, I can rotate it, twist it, I can add more if I want, probably a lot more. I can, of course, change my camera, but I won't see this thing. So yeah, for example, the great thing with it is everything is generated in your graphics card. So from all these points, as I said here, now it's how many control points? It's 64 by 382. So well, it's quite a lot. It's 25,000 control points, but then I generate 1 million primitive out of it from pretty much nothing. So and it didn't left the graphics card, I didn't have to do anything. It's all generated on the fly every frame, which is quite pretty amazing. So yeah, you can do quite tessellation is quite a really also nice feature for all this kind of more abstract graphics. One other example, which is a very one which a lot of people from demo scene are quite fun. So is you take take a box like this and I just put it into. So here, if I put it in wireframe, so that's my low resolution. If I put it in wireframe, that's my box. And now I can dynamically increase the resolution of my box. And that means as soon as like if, for example, if I put it with low res and I start to distort it, you can really see this kind of horrible angles around. So you can see this horrible, and now if I do this, it just like smoothes it on the fly. So it's the same. I just start with like a few amount of boxes and just using tessellation and a couple of distortion function. It's just basically a rotation. It's like not even. I think a kid from GCSE could probably do that. But yeah, you can achieve some quite interesting results. So now, yeah, now we've seen we're using instancing and we're generating geometry on the fly. And I was speaking about culling before. Problem now is like previous demo was using CPU, and now we generated a lot of geometry in my graphics card, so I don't want to get it back. And so I need to do curl, but I'm gonna do it now in graphics card. So we use compute shader, like it's just pretty much amazing unit, and we create a buffer which is called append buffer. So it's a buffer which has, it's just a flag basically, which means it will have an internal counter. So we just send the bounding box and the transform into the buffer. And we create a new buffer which says this, which only includes objects which pass the test. Cool. So, like in this one, for example, now my geometry is in buffer. It's like 64,000 spheres, so it's not that many. And now you can see also there's like a timer, so I can know how much shader, how much time takes every unit. So for example here we have 16 milliseconds of rendering for everything, and that's the test for the curl, which is half a millisecond. And now if I say I want to curl, I already cut it in half. So how it works is really super simple. It's like I get the bounding box, I test the bounding box against the plane that I retrieve from the camera here, and I say append the number, append the object number. It's not append I don't want to reappend all the object material data because it's too much data to move around, so we can just use, say, your sphere number 1 passed the test. But now we run into a little issue. It's like, now we have, like, from a static amount of objects. So before I could happily say, draw me 64,000 sphere, but now I don't know how much sphere I need to render anymore because some have passed the test and some have not passed the test. So that's, before you had to use query, which is a bit of a problem, and now what you can do is to send the draw instruction. We're going to use actually the GPU data. So it's like we have append buffer with the internal counter, so every frame I reset it and it's increased by 1 for every object that passed the test. I do my compute shader dispatch, and there's an instruction which is called copy structure count in DirectX, which means copy the counter into an indirect buffer. So it's a little GPU buffer which is exactly the same as you would do, and then you can say draw indirect, and so I can bind the append buffer as before. So now it's like, so without the curl, that's my, so I have my world transform, and that's the index. So I get the world multiply, and now I get Instead, I do a lookup on the object that passes the test and then get this from the index here. So it's just a little lookup table. But yeah, it's quite really, like in that case also, it's a kind of worst case scenario because I got a lot of objects bound together. But if you have a very like large scene, you can have like really significant gain from it. You can really see, yeah, in some, you can go easily from 50 to 100%. Like here now I'm at 350 frames a second, so it's quite. So it's like, you know, you can use pipeline, like that's what one of the major advances. Before you had to use shaders to only for creating graphics. Now you can use them to all this kind of different purpose. So you can use it for geometry optimization. You can do a lot more compared to before. So now I show this one is a bit fancy so also. So like now I'm going to show like a ring buffer. So before you had to use texture, draw everything, generate editor, process every pixel, every frame, every object. Now we can also say, look, the problem with pixel is you can't tell where to write. You have to say process. You can only tell where to write. Whereas with buffer you can do scattered write. So that's like a little ring buffer example. So you can, yeah, you can change a bit. Like this one has like mostly full deferred, so it has like it's the same as before. Like I render this really lovely texture at the beginning. That's how it looks like. And then you, like if I remove them actually, it's so you start with this. You add 120 point lights. Still looks kind of ugly. Then you add occlusion, it looks a bit nicer. Then you add some depth of field. We don't, yeah. And you add tone map because the rendering is in HDR as well. And yeah, some FXAA for fixing the aliasing a bit. So now, yeah, that's how, like before for a ring buffer with this amount of object, it will take about something like, I don't know, 2-3 milliseconds. Now it takes 0.05 milliseconds. So what we do is like I emit like not many objects at the same time. Actually, I emit about 100 objects, and because I'm allowed to say just where to write. So before we had to do, I don't have a sample, but it's basically what is the emitter now, which is just like we can just say write here instead of. So we can save right, for example, at position 1000, even if we pixel number 1. With pixels before, we always had to use 2. So we can do like simple algorithm like this in a very, very efficient way. And because it's instance, I don't have to replicate the geometry, so it might be a bit high for spheres. So I can also, because everything is stream, if you don't like boxes, you can change it to a sphere instead. And it's done like this because I don't generate 1000 spheres, it's always streamed. And yeah, it's running, I don't know what the frame rate is. So yeah, it's pushing 5 million polygons around, and it's probably running, yeah, it's running at 55, so it's kind of, you can quite push a lot of geometry now with this card. So yeah, the sticks are all generated in the same, it's a null drawer, and I generate the line to tube in geometry shader. So now we do something quite a bit more fun. So now we're going to do picking because it's quite fun to draw objects, but now we kind of want to interact with them. So to do picking, like we need to check the intersection with objects. So in that case, I'm going to raycast. You mark any object which is being touched as held, and you animate every touched object in whatever animation technique you want. So you can attach a spring or do anything. So it's a bit the same as doing buffer. So we create a buffer, then I do an intersection test. So it's like, in this case, I convert the mouse position into a ray, and then I do a ray test on the object. And now we have a buffer which we say this is the object hit, and call the animation routine only with that number of objects, because objects that are not touched, there's no point of say move them of 0. So we try to always reduce the set of data we're working with. But you'll see there's a little but. Where is it? So yeah, it's like, so I have 1 million boxes. And now I just like do 1 million raycast when I click on the mouse. So you can just like every object which is hit is like moved upward, so you can do like switches if you want. And now so for doing the ray, it's like I got my ray, I get the I get an approximation of the box, and I do a like simple ray test, like the most basic ray intersection in the world. And I say if the object intersects the sphere, like that means this object is picked and needs to be animated. So now, like before, when I was doing drawing, I could just use this copy structure count. That means, oh, I got 20 objects in my buffer, so draw 20 objects. The problem is with the compute shader, you have something which is called warp size, which is this number here. So that means I need to say, process this amount divided by this amount. So that creates a little problem now, because I got a variable amount of objects, and copy structure count sends the exact number of objects, and dispatch has this thing which is called warp size, which is what makes it efficient. So how are we going to do that? There's of course a solution, but I might start to lose you a bit now, if I didn't lose you already. So we're going to use a technique which is called indirect dispatch. So that means we do it, like when we do a dispatch call, it's like when we process a shader, so we're going to do a dispatch call to generate a dispatch call. Does it make sense? No. So we use copy structure count into a small buffer as before, and then we use it, like we send it into a small compute shader which will process only 1 unit, read the value from there, divide by warp size, and then we write into that buffer. So that's basically what we do here, which is like indirect dispatcher. So I retrieve from the buffer here, I retrieve the structure count, which I copy in the buffer, and then this like little piece here, which generates a dispatch call, is basically just you do a call to generate a call. It feels a bit weird, but that's a really powerful feature technically. So it allows you to do all this when you, like for pretty much any dynamic particle system, it's completely, like it's fundamental for this type of graphics. So yeah, you can play around with it. And the great advantage is, yeah, because of that, I only process, like I can actually know my counts, so if I check on my tester, that's technically good. So for example, I process only, out of 1 million, I process 5,000 objects, which is quite very good compression ratio. So performance-wise, it's well, it gives quite an obviously massive gain. So it's almost done, I think. Yeah, so that's pretty much done. So there's a lot of different other techniques you can use. Like, for example, we use compute, for example, to generate particles out of model. I don't think I have this around now. So that's like a very basic one. So for example, there's no shading or anything. So that I take this model, which normally is, if I go back and set, so that's like every time I get a point, but now you can see my model will look kind of ugly as particles. So I just select it a bit as much as I want, and then you can apply some random animation on top of it. This one has no shading, which is of course nicer with it. You can apply like fake gravity, or so that's like some other simple example you can do. So I think that's about it. So quite a few things around when you do graphics quickly, and that will finish I will finish this way. So yeah, the first thing is profile your code always. So like queries like timestamp, you need to use them everywhere because you need to really know everything about how it executes. Occlusion queries, pipeline statistics are totally fundamental for the graphics, so they are totally implemented. Often when you do like texture lookup, it costs. So a lot of people use a circle texture for doing for particles, and you can do in one line of code that a 12-year-old kid could do. You can just, like I did a demo with 11 million, like it goes from 12 milliseconds to 3 milliseconds. It's basically one multiplication, and you can generate a circle in pixel shader, so don't even bother to do this kind of thing. Geometry shader is very flexible unit. It's really amazing unit. It's like you abuse it for prototyping because it's just great, but it's very bad on parallel work, so it's very slow. So normally you keep it to a minimum for the work. It's the only case where it's really nice, it's for point to quad, which is like the standard particle generation. So in that case you can really abuse it, but in most of the case you really need to keep it easy with it. And same with instancing, like if you do very, like for example, if you just send one triangle with a huge number of particles, you're gonna blow up your graphics card without having time to see it. So like null draw on vertex ID is like a much nicer way. So yeah, so that's pretty much it. Like now, actually I'm doing a presentation of DX11, but there's DX11.1. So what's a bit new into there? Well, there's a very interesting thing is now you can use these buffers in every stage of the pipeline. So you can, like for generative graphics, it's just a godsend. It's going to be Windows 8 only, which is a tiny bit annoying in some way because, well, that means move all your development environment, which can create issues. There's a few things they decided to do which are not very nice, and it should be also have 3D support out of the box, but I've not tested it yet. So that's like about it. So if you have some questions, you are more than welcome, and thanks for listening. Anyone got a question?
Stupid quick one. You've seen all the numbers, but what graphics card is it actually running on?
That's 670, which is like pretty, for this size of machine, it's the best one you can get. 680 is a bit better, but not that much. But 670 is like, yeah, doing some very good job compared to a laptop.
So I guess a lot of the nodes that you were demonstrating tonight, the majority of most 4V users won't go inside of them, but people that did want to go and make their own DirectX 11 nodes, do you have any reading material that you recommend?
Well, there's a lot of problem is a lot of material is designed. There's no like middle ground with graphics because it's mostly used by the game industry. So you have quite either like super basic example or extremely advanced example. There's not that much middle ground. There's all the samples in the NVIDIA SDK, which some of them are quite nice, some of them are completely unreadable. And there's a few blogs for some graphics programmer which are quite nice. I could post them around because yeah, there's quite a lot of there's a lot of new features and it's a bit of a different way to work compared to before.
And do you work mostly or only with 4V? Or?
Not only, I also got a bit my own tool that I write, which is a bit working differently from 4V, but which is not very advanced yet, but it's running 11 as well, but it's running in a different concept of it. And I used Cinder a tiny bit, but yeah, it's just like most of the time I get enough spare for my stuff running 4V, so it's like I use a lot of programming because obviously all these nodes are programmed either in C# or C++, so I use plain C# or C++ a lot, of course. So thank you.